Space is staggeringly empty. The distances between stars are so vast, it's almost mathematically impossible for a stray object to casually cross solar systems. But in the summer of 2025, an object designated 3I/Atlas broke that cosmic silence and entered our neighborhood. This map traces its arrival. You can see it piercing straight through our outer orbital rings at an extreme velocity of 36 miles per second. At its core, 3I/Atlas is a primordial snowball, a loose collection of rock, dust, and ice locked in a deep freeze for billions of years. Its extreme speed and straight-line trajectory mark it as an unbound interstellar interloper rather than a local comet, a once-in-a-lifetime target for human observation. Following this trajectory model into October 2025, the comet takes a direct perilous dive toward the Sun. This ancient relic, accustomed to the absolute zero of deep space, was about to plunge into a literal blast furnace. Astronomers expected the intense heat and gravitational stress to completely shatter and vaporize the fragile ice block. Against all odds, it survived the gauntlet. It emerged from the Sun's glare glowing brilliantly, shedding massive amounts of vapor and dust, yet remaining structurally intact. That survival turned a brief astronomical observation into an urgent ticking clock emergency for every major telescope on Earth. Once the comet survived the Sun, the global astronomical community realized their window to observe it was rapidly closing. Its outbound flight path pushed it past Venus in November and rocketed it toward a close Earth approach in December 2025, passing just 167 million miles away. This triggered a frantic global scramble to pivot humanity's greatest observational instruments to catch the comet in this narrow window. The James Webb Space Telescope locked on, capturing deep infrared data from the comet's glowing tail. At the exact same time, the Autoconal Large Millimeter Array dialed into the comet's radio frequencies to measure its chemical outgassing. This coordinated multi-telescope effort represented our one and only chance to interrogate this visitor before it vanishes back into the void. They analyzed it using spectroscopy, decoding the light passing through the shedding dust to read the comet's chemical makeup like a barcode. The spectra revealed an unexpected chemical profile: methane, and a highly unusual concentration of semi-heavy water. Semi-heavy water contains deuterium, which is simply a heavier, naturally occurring isotope of hydrogen. This chart illustrates the anomaly. The JWST data proves 3I/Atlas contains a deuterium to normal hydrogen ratio 40 times higher than what is found anywhere on Earth. The data revealed a second anomaly. The chemical signature completely lacked the isotope carbon-13. Carbon-13 is a marker of time. It slowly accumulates in galactic gas clouds as generations of stars live and die. Its absence suggests 3I/Atlas formed in a pristine environment, long before the universe was old enough to be saturated with these heavier atoms. By March 2026, the comet passed the orbit of Jupiter, marking the definitive end of our prime observational window. This projection shows the mechanics of its escape. The Sun's gravity is mathematically insufficient to tether or slow an object moving with this much momentum. 3I/Atlas is now on an irreversible escape trajectory, heading back into the interstellar void forever. A moment of wonder. Our entire 4.6 billion-year-old solar system was merely a brief, fiery pit stop for this wanderer. Because carbon-13 takes billions of years to build up in a galaxy, its total absence proves that 3I/Atlas is a 10 to 12 billion-year-old time capsule, meaning it predates our own sun and even our region of the Milky Way. Humanity managed to scramble and successfully read a single page from a 12 billion-year-old history book before the cosmic wind blew it away. If this ancient relic survived a 10 billion-year journey just across our path, what else is currently coasting through the dark?